Okay, Chapter 3, Section 2 is about logarithmic functions. We just talked about exponential functions in Section 1. Logs are the inverse operation to exponential functions. We talked about this back in college algebra. So if you've got logarithmic form, it's going to be log base a of some number, we'll call the argument, is going to be equal to some number which will be the exponent on the a that created that argument. So your equivalent exponential form then is going to be the base raised to the exponent is equal to that argument, which is right here. So what you just need to be able to do is identify the base and the exponent and the argument. So the base in exponential form raised to the exponent will equal the argument. And if I want to convert to logarithmic form, we'll have log of this base argument is equal to the exponent. Okay, sometimes converting from one form to another can actually help you solve problems. So let's go ahead and write the expression in equivalent exponential form. We need to identify what the base is, what the argument is, and what the exponent is. So the base in this case is going to be a 27, found right here. And the argument is this 3. And the exponent is the 1/3. So if we want to put this in exponential form, it will be the base raised to the exponent, which is equal to the argument. So what this is saying is the cube root of 27 is equal to 3, and that is correct. Write the expression in equivalent exponential form. Opposite of the log base b of the argument is equal to w. So then base is going to be b, argument is going to be b, and the exponent is going to be w. So the opposite of b raised to the exponent will be equal to the argument. Write the equivalent logarithmic form of 10 to the negative 2 power is equal to 0.01. Base in this case is the 10. The argument is the 0.01. And the exponent is the negative 2. So it's going to be log of the base, which is 10, of the argument, which is the 0.01, is equal to the exponent, which is negative 2. Now, if you recall back to your college algebra, log base 10 was called the common log. It's actually a button on your calculator. They don't have log base anything right on the face of the calculator, but they do have logs, which means common logs. So if you saw this expressed, you would automatically know that the base is 10. All right, we have one more on this page that says write the equivalent logarithmic form of q to the n power is equal to t. First thing I need is the base. The base is right here, it's q. Then I'm going to need the argument. The argument's over here, it's t. Is equal to the exponent, which is right there, and that's going to be n. Okay, now remember, your base has to be a positive number. It cannot be 1. And your argument also has to be a positive number because any positive number raised to a power is going to give you back a positive number. All right, so then let's use this information to solve for x. I have log base x of 64 is equal to 3. So converting this from logarithmic to exponential could potentially help me solve this. So let's give it a shot. This says x cubed is equal to 64. If you cube root both sides, the cube root of x cubed will be x, and then the cube root of 64 is 4. So log base 4 of 64 is 3, or in other words, 4 cubed is equal to 64. For the next example, it says solve for x. I have log base 6 of x is equal to negative 1. Let's convert this to exponential form. The base is 6, the power is negative 1, the argument is going to be x. So then if we rewrite this without the negative exponent, it's just going to be x is equal to 1 over 6 to the positive 1, which is just 1/6. All right. Properties of logarithms, if you recall. If you have a product that you are taking the logarithm of, you can split it into a sum of the logarithms of its factors. If you have a quotient, you are able to split it into the difference of the logarithm of the numerator and denominator. If you have a log raised, the argument raised to a power, the power actually comes out front as a factor, and log base a of m to the k factor is the same as k times log base a of just m. Now, log base a of a, so anything to the first power is itself is what that's saying. And then log base a of 1 is equal to 0, so anything to the 0 power is always 1. If you need to change the base, before we had calculators that couldn't do anything other than log base 10 and log base e, so which are natural logs, which are the ln's, so we have to convert them. So the change of base formula is log base b of m is equal to log of the new base of the old argument divided by log of the new base of the old base. So notation for log base e is actually ln. It's called the natural log, and common logs are log base 10, and just write the word log. Okay, we are given that the log of some base b of the number 3 is 1.099, and we're also given that the log of that same base b of the number 5 is 1.609. So in other words, b raised to the 1.099 power will return a 3, and b raised to the 1.609 power will return a 5. Find log base b of 1/5. Hint, use the quotient property. Okay, quotient property says I'm going to turn my fraction into subtraction. So this will be log base b of 1 minus log base b of 5. And we've been given numbers for these because anything to the 0 power is 1. So this is going to be a 0 power minus, they've given us a value up here of 1.609. So this is going to be equal to negative 1.609. Okay. For the next one, they have the same values. This time we're doing log base b of the square root of b cubed. Hint, use the exponential property. Let's rewrite this as a rational exponent first of all. So log base b of b, now exponential rational exponent means the power is 3, the index is 2. This is a 3/2. Now the exponent property says that the exponent comes out front as a factor. So 3/2 of log base b of b. We had a rule that said log base b of b is 1. So it's anything to the first power is itself. So this is just equal to 3/2. And it makes sense. If I'm asking you what exponent I used to create b to 3/2 power, it has to be the same exponent to make that happen. All right, let's try this one. Same values again. This time we're trying to do log base b of 75. Now, the numbers I have to use are 1, b itself, 3 and 5, that's it. So the only thing that's going to help me, I think, are the 5s with this. So we're going to write, well, actually in the 3, log base b, 75, we'll turn that into 3 times 25, and 25 is 3 times 5 squared. From here, I'm going to be able to use the product property, and from there, I'm going to be able to use the exponent property. So this is going to be log base b of 3 plus log base b of 5 squared, which is going to be log base b of 3 plus 2 times log base b of 5. And they gave us numerical values, so the first one would be 1.099 plus 2 times 1.609 is equal to, and when we multiply and then add, should be 4.317. Okay. It says use logs to bring variables out of the exponent position and down into the problem. If you have an e, actually, when you do these problems, you're best off to use natural log unless you have a common log situation. So since the t is in the exponent position and I want to get to it, I'm going to take the natural log of both sides. So natural log of e to the t power is going to be equal to the natural log of 10. The exponential property says t times ln e is equal to ln 10. ln e is just 1 because anything to the first power is itself, and 1 times t is t. So as an exact answer, t is equal to the natural log of 10. If I want to put this in the calculator, it will give me an approximation. I've rounded, and it will be 2.3. So ln 10 is exact, and 2.3 is an approximation. For the next one, says solve for t. Again, we've got that base e and our variables up in the exponent position. So natural log of e to the 0.07t is equal to the natural log of 2. We already know that this is going to be 0.07t is equal to natural log of 2. If we divide the 0.07 away, t is equal to the natural log of 2 divided by 0.07. So this is your exact answer. If you want to throw this in a calculator, it is approximately 9.9. And this is your approximation. Okay. So that was from college algebra. Let's go now back to our calculus, and we're going to work with derivatives. The derivative of the natural log function is 1 over x. So d dx of ln x is 1 over x. Now, if the x value here, the argument, happens to be an expression other than x, then you're going to use your chain rule. It'll be 1 over whatever the argument is times the derivative of the argument. Okay, so for our first example, it says differentiate. So dy dx will be equal to -9 times the derivative of ln x, which is 1 over x. So it's going to be -9 over x. For our second one, our second example, looks like we've got product rule here. So dy dx is going to be equal to the first times the derivative of the second. Derivative of ln x is 1 over x, plus the second, ln x, times the derivative of the first, which will be 6x to the 5th power, minus the derivative of the second term. So 4 times 1/4 is 1, x cubed. Okay, so let's clean this up a little bit, which is going to be, this is going to cancel with one of these, making this x to the 5th, plus 6x to the 5th ln x minus x cubed. Okay, let's go ahead and do the derivative. Notice that we have a quotient, which means we can use the formula for quotient property of logs here. Let's split this up. It's going to be the natural log of x squared plus 5 minus the natural log of x. That way we don't have to use quotient rule when we do the derivative. So f prime of x will be equal to 1 over the argument times derivative of the argument, which is just 2x, minus derivative of ln x is 1 over x. Okay, so then this is just going to be 2x over x squared plus 5 minus 1 over x. If we were to find a common denominator and simplify this so that it's one fraction, we would have to multiply this fraction by x over x, and we would have to multiply this fraction by x squared plus 5 over itself. Okay, so then this is going to be 2x squared minus x squared minus 5 all over x times x squared plus 5. 2x squared minus x squared is going to be x squared minus 5 over x times x squared plus 5, and that's as far as we'll be able to go with that. We aren't going to be able to cancel anything. Okay, a model for consumers' response to advertising is given by N of A is equal to 2,000 plus 500 ln A. A is greater than or equal to 1, where N of A is the number of units sold and A is the amount spent on advertising in thousands of dollars. How many units were sold after spending $1,000 on advertising? So A is in thousands, we're spending 1,000, so A is going to be equal to 1. So N of 1 will be equal to 2,000 plus 500 times the natural log of 1, which happens to be 0, because anything to the 0 power is 1. So 0 times 500 is 0, so this is just 2,000. Okay, so we'd be selling 2,000 items. Find the derivative of your function. So for b, n prime of a is going to be equal to, derivative of 2,000 is going to be 0 plus 500 times the derivative of ln a, which is 1 over a. So this is going to be 500 over a. Then find n prime of 10. So n prime of 10 is equal to 500 divided by 10, which is then going to be equal to 50. Okay, so then we've got a rate of change when we spend 10,000 of 50 units. Okay, per thousand. Find the maximum and minimum values if they exist. So then, if we're looking for a max min here, then we need to find our critical values. And since our derivative fails
to exist, so that's our critical value.
Okay, then let's test. See if we spend no money. Maybe it's a maximum or minimum value. So since I can't, let's see, if we test to the -1, let's do this. We'll test -1 and +1. Not that -1 makes much sense, but let's go ahead and test it. So n prime of -1 would be equal to 500 over -1, which is -500. So here we are decreasing. And n prime of +1 is 500 over 1, which is 500, which is positive. So on the right side we are increasing, which means at 0 there would be a minimum value. And there would be no max.